Ever since the first tools and utensils were fashioned from raw materials, we have looked for ways to improve our creations. For centuries, artisans, manufacturers, engineers, and scientists have manipulated the materials they've worked with to make better products. In doing this, they've controlled or changed such things as temperature, pressure, and composition. But during all that time, the one part of their equation over which they've had no control is the constant pull of It should come as no surprise that we live in a world dominated by gravity. Gravity is a constant. Besides keeping us from falling off the planet, gravity also makes many of the things in our life work the way they do. But gravity also imposes many restrictions, especially in some forms of scientific research. Obviously, there's no giant switch we can flip to turn off gravity, but there is a way to escape its effects.
Columbia, Houston, we're about 1 minute to LOS. You have a go to ingress space lab.
Space-based laboratories like this one on the space shuttle offer scientists a new research environment. That's because in a microgravity laboratory, the effect of gravity is no longer a constant, and that means exciting new research opportunities are available to scientists in several fields of study. NASA's microgravity research program is primarily interested in 4 scientific disciplines: biotechnology, combustion science, fluid physics, and materials science. We'll look in on some of these high-flying investigations in a minute, but before we do, there are a few questions we need to answer. Questions like, what is microgravity? Why do we go to space to achieve it? And why is microgravity ideal for conducting many types of scientific investigations? Let's start by defining microgravity. The strange environment that astronauts experience in space is often called zero gravity, but that term is technically incorrect. Why? Because even 300 kilometers out in space, gravity still exerts over 90% of the attractive force it has at the Earth's surface. What astronauts experience on a spacecraft orbiting the Earth is microgravity, which is an environment where the pull of gravity seems small compared to what we feel on the ground. Microgravity in Earth orbit is really a result of free fall. Here's what I mean. Imagine yourself in an elevator riding to the top of a tall building. Just before reaching the top, the cable snaps and your car begins falling. As you free fall toward the ground, you, the elevator car, and everything inside are accelerating at the same rate due to the pull of gravity. Everything seems to float, and for a brief period, the effects of gravity seem to disappear. That's exactly what's happening on the space shuttle, all except for the sudden stop. Once the shuttle reaches orbit, it's traveling fast enough to maintain a constant free fall around the Earth. The free fall, in turn, creates the microgravity conditions that make things look like they're floating when really they're falling. We experience short durations of microgravity ourselves each time we ride a roller coaster, jump on a trampoline, or dive off a diving board. Over 200 years ago, William Watts learned that he could make better musket balls by dropping molten lead from a tall tower. Since then, scientists have continued the use of freefall for research with taller, more sophisticated drop towers, research aircraft like NASA's KC-135, and suborbital rockets. But even with these advancements in technology, periods of freefall for research are limited to less than about 10 minutes.
And that's the answer to our second question. We go to space to achieve longer durations of microgravity.
On the space shuttle, scientists can experience more than 2 weeks of microgravity to conduct their research. And a space station will mean permanent microgravity research facilities.
Now that we know what microgravity is and why we go to space to achieve it, let's find out why it's such a good environment for scientific research.
In large part, it has to do with fluids and how they're affected by gravity. Fluids are any gases or liquids that will flow and assume the shape of their container. From the silicon chips that drive our high-tech society to important medical research crystals grown from solution, to the combustion process that is so important to our society, fluids, in one form or another, affect us all.
But what does gravity have to do with all of this? Plenty. Watch.
Atoms, molecules, and particles move in fluids by means of several transport mechanisms. But two of these mechanisms, sedimentation and buoyancy-driven convection, dominate on Earth because they are caused by gravity. An example of sedimentation is what happens when fluids of unequal density are combined. Gravity causes the fluids to settle in layers, with the heaviest, most dense fluid on the bottom and the lightest, least dense fluid on top. The other phenomenon, buoyancy-driven convection, can occur when the temperature of a fluid changes, causing changes in its density. For example, when heat is placed under a beaker of water, the water at the bottom expands as it gets warmer, becoming less dense. Gravity then pulls the cooler, denser water at the top toward the bottom, where the cycle is repeated. There are other fluid transport mechanisms that are not as affected by gravity. One is called diffusion. Diffusion occurs because atoms in a highly concentrated region naturally tend to move to regions of lower concentration. When this small container of colored water is placed into a larger container of plain water, the colored water begins to move, or diffuse, to less concentrated areas until the two liquids are evenly distributed. Another way to create flow in liquids is to cause the surface tension to vary from one point on the surface to another. Every liquid has surface tension. It is a result of the force which attracts a liquid's molecules to each other. The surface tension of water is great enough that a needle can rest on the surface. But surface tension can change. By adding a surfactant, in this case a drop of soap, the surface tension of the water changes enough that it will no longer support the needle. Another way to change surface tension is by changing the temperature of the liquid. Watch how the oil in this pan responds to the change in temperature. These movements are called surface tension-driven flows. The final mechanism we'll talk about is capillarity, which is closely related to surface tension. Capillarity can be described as the attraction a fluid has for itself versus the attraction it has for a solid surface. When a small diameter capillary tube is placed in colored water, we can see that the water rises high into the tube. But do the same thing with a different liquid and it will not rise as high. That's because the capillary forces are different in each case. Unfortunately, for scientists and others who work with fluids, sedimentation and buoyancy-driven convection dominate experiments involving fluids of different densities and experiments where temperature changes are involved. And because sedimentation and buoyancy-driven convection are dominant on Earth, they can mask or hide the true behavior of other transport mechanisms that fluid physicists are trying to better understand.
Still Space Lab 0.57 now.
So to answer our third question, the reason microgravity is such an ideal place for scientific research is that its low gravity conditions virtually eliminate sedimentation and buoyancy-driven convection. Okay, now we know what microgravity is, why we go to space to achieve it, and why it's such a good place for scientific research. So now let's look at some experiments conducted in space and see what kind of a difference microgravity makes. Let's begin with a fluid physics investigation.
On Earth, we think of a liquid in the form of drops, streams, puddles, or simply the shape of the container it occupies. But in microgravity, liquids enter a completely new realm. Free from the effects of Earth's gravity, surface tension takes over, forming the liquid into a near-perfect sphere. It is now a self-contained volume of liquid, free-falling with the rest of the shuttle's cargo. This sphere of liquid is part of a fluid physics experiment which uses the drop physics module. The drop is suspended because it's free-falling, but the movement we see is caused by sound waves used to maneuver the drop. These one-of-a-kind experiments enable fluid physicists to test hypotheses made on the ground. Experiments like these, impossible to perform on Earth, are also helping scientists to assess the potential benefits of containerless processing techniques, among other things.
This important part of the research process provides scientists with a compass to keep their research headed in the right direction. The information obtained by fluid physics research can be applied to all disciplines that involve fluids. One such area is biotechnology.
Protein crystals are an important biotechnology tool in the development of more effective medicines. Proteins control the chemical reactions essential for all processes in the human body. Misbehaving proteins can cause disease. The detailed study of a misbehaving protein structure can lead to the design of a drug to counteract its disease-causing behavior. Protein crystals are grown to understand the three-dimensional molecular structure of proteins. To obtain this structure, the protein crystal is exposed to X-rays. X-rays bounce off the atoms in the protein crystal, forming a complex image called the diffraction pattern. The details of this pattern are determined by the location of the protein's atoms. Researchers then interpret this pattern with a computer where a three-dimensional model of the protein is created. Especially important areas of the protein structure to be determined are those called binding sites. This is the place where drugs attach to the protein to correct its misbehavior. Scientists can then use the model and the shape of the binding sites to design better pharmaceuticals.
It all sounds simple enough, except protein crystals are typically grown from solution, a process that involves fluids and changes in density. That combination means that many crystals grown on Earth have gravity-induced defects that interfere in the precise determination of the protein structure. In a ground-based laboratory, sedimentation and buoyancy-driven convection can disrupt the growth process, which may prevent quality crystals from forming.
But in a microgravity laboratory, essentially free from gravity-driven phenomena, superior crystals have been produced. On one Space Shuttle microgravity laboratory, the most perfect malic enzyme crystal ever was grown. This after years of unsuccessful attempts on Earth.
Now, researchers may be able to determine the structure of this important protein for the first time. This achievement hopefully will lead to the development of more effective antiparasitic drugs.
Another Space Shuttle microgravity mission yielded crystals of the satellite tobacco mosaic virus with such high resolution that a scientist could visualize the structure of the virus's nucleic acid to an extent not seen before. Being able to better understand viruses in agriculture products like tobacco will also help farmers to increase their production of food crops. The process of creating crystals is called crystallization, and it also plays a major role in microgravity material science research. The atoms that make up solid matter can have either a crystalline or non-crystalline arrangement. Crystalline matter is the most common. It includes metals such as copper, steel, and lead, ceramics, and semiconductor materials such as silicon. The atoms that make up crystalline matter are ordered on planes stacked together in a regular pattern. Even though crystalline materials are solid, they were once a fluid and susceptible to gravity-driven forces as they transform from the fluid to the solid state. In the case of semiconductor chips and high-speed processors, like those made from thin wafers of silicon, this poses limitations in the manufacturing process. That's because the more control that engineers have over how the atoms are arranged, the more that can be done with the crystal.
But with buoyancy-driven convection present when a crystal is grown on Earth from fluids, it's difficult to determine how gravity affects its degree of crystalline perfection.
On the shuttle, one type of crystal growth process begins with a container filled with a solution. In the liquid, protected by an enclosure, is a small seed crystal. The seed is exposed to the solution, and the temperature of the crystal is lowered. As the solution near the crystal cools, the dissolved material reaches the saturation limit and begins depositing on the seed. This causes the seed to grow. As this happens, solute is depleted in the region near the crystal. Microgravity experiments are also a window to other material science processes. For example, on Earth it is virtually impossible to combine some metals of different densities into an alloy that is useful. Sedimentation will cause the metals to settle before they solidify. In space, where sedimentation is no longer a factor, new alloy structures and superalloys may be possible. But that's not all. Continued material science research in microgravity laboratories promises to help redefine what is possible when solids form from a fluid state. Microgravity investigations are also aimed at understanding the combustion process.
A candle is an excellent example of the fluid transport mechanisms at work in the combustion process as it occurs in gravity.
The heat produced by the flame melts the wax at the base of the wick. The wax, now a liquid, rises up the wick. As the liquid wax moves closer to the flame, it vaporizes and mixes with oxygen at the flame surface. The products of this chemical reaction are heated and become buoyant. As they are carried upward and away, convective forces move fresh oxygen toward the flame. Convective forces are also at work in the space between the wick and the flame surface, where solid particles of soot are convected upward as well. At the flame's tip, some of these particles burn off with a bright yellow color. To overcome the loss of heat, the flame moves closer to the wick. The combination of these effects gives the flame its familiar teardrop shape. Now that we know how the combustion process works on Earth, how will it function in microgravity, where buoyancy-driven convection is virtually eliminated? What will the flame look like? How long will it burn? Or will it even burn at all? Let's see. As this burning candle reveals, the virtual absence of gravity-driven convection radically changes the appearance of the flame. Without buoyancy-driven convection, the flame must rely on the much slower process of diffusion to transport oxygen and fuel vapor. With no up for the heated reaction products to be drawn to, the flame assumes a spherical shape. Heat is lost to the candle, which reduces the amount of liquid wax to be vaporized into fuel. This quenches the bottom of the flame to where only part of the sphere is visible. The reduced rate of oxygen and fuel vapor transported to the flame because of these effects also affects how long the candle will burn. Studies like these help designers of spacecraft better understand the burning process in low gravity so that they can even more effectively safeguard against fire. but there are also ground-based benefits as well. Increased knowledge of the combustion process could lead to improved methods for fighting the uncontrolled fires that destroy lives and property each year. Combustion also affects us in other ways. Soot formed in the combustion process is a major contributor to pollution on this planet. By studying combustion and microgravity, where larger primary soot particles and much larger aggregates are formed, scientists may find clues to reducing the amount of pollution that results from the combustion process here on the ground.
It's true that we live in a world dominated by gravity, but in just the past few minutes we've taken a glimpse at how the microgravity of Earth orbit is eliminating obstacles that have limited research and development for centuries.
Access to space has opened a new era of discovery for modern-day explorers and scientists. But space travel is not only about finding new worlds or navigating the cosmos, it's also about unlocking the secrets of our own planet and making life better here.
The future holds even greater promise, but not unless people just like you are prepared to become the scientists, engineers, and mathematicians of tomorrow, ready to ask questions, to seek answers, and expand the scope of human knowledge. The real question is, are you up to the challenge?